So the fourth talk in this session is one of the quantum papers that was submitted to PLDI this year. The title is An Automata-Based Framework for Verification and Bug Hunting in Quantum Circuits. It'll be presented by Yu-Fang Chen from Academia Sinica in Taiwan, and his co-authors are Chung, Ondřej Lengál, Jyun-Ao, Wei-Lun Tsai, and Yen.
Yeah. Thanks for the introduction. I'm Yu-Fang Chen from Academia Sinica. And actually, from here, you can see that every people with hyphen there are from the same institution. And the only exception is Ondřej is from Czech Republic, Brno University of Technology. First thing to say is don't be scared, because usually in the conference, if you see the two dangerous keywords, like automata and half people left, and quantum the other half. So don't be scared, don't run away. I will give you all the required background in this talk. I'll make it accessible to verification people. So let's begin with this. So why is a 3-bit classical state? It's very simple, just a Boolean assignment. Like, for example, this 0, 1, 0. This is a classical state of 3-bit. So why is a quantum state? Okay, it's actually something very similar, just like it's a distribution over classical state. Like in this case, this state has 0, 0, 0, maybe 5% opportunity if you observe it. 0, 0, 1 is 2.5%, etc. So it's just a probabilistic distribution over all classical states. So you can build actually a quantum state as a decision tree where, I should use a pointer. Where each branch actually corresponds to a classical state, 0, 0, 1, and probability C1. 0, 0, 1 is probability C1, yeah. So message 1, a quantum state is a decision tree. So in classical computing, we have the gate to and or not gate to change the classical state. That's how state transform. In quantum, we have a counterpart. We have quantum gate. For example, this X gate, it's actually the negation gate in quantum. It's actually, we can view it just as a tree transformation. So it's update the tree. In this case, if I apply S gate on the first qubit, what happens is that it swaps the left and right subtree. So the red subtree is moved from the left to right, and green one to the left. That's the quantum gate. So message 2, quantum gate is just a tree transformation. So quantum circuit, why is this quantum circuit? It's just a sequence of quantum gate, like written in this way. So gate 1, gate 2, like S gate on the first qubit, S gate on the second qubit, etc. So it's just a sequence of gate operations. That's how your state changes. Just a sequence without branching, no branching. So that's a quantum circuit. Okay, now you get all the quantum background you need for this talk. Why we are interested in verify this kind of circuit? It's just a sequential program, nothing difficult. Actually, this is because in quantum computer, you need to do the so-called compilation. So you compile from the, say, textbook algorithm to the gate supported and the structure supported by your quantum computer. And the compiled code is completely unreadable. It's very difficult to ensure its correctness. So we need a way to do this. And also, testing like a traditional way to ensure software quality is not so feasible in quantum setting. Because when you run a circuit in a quantum computer, every time you just, at the end, you get a value, a classical value, depending on the distribution of your final quantum state. It can happen at the first time, also it's the same quantum state, but for the first time that you observe it, you get the 0, 1, 1, and the second time you get the 1, 0, 0 according to this distribution. So testing is not so feasible. So we need a better way. And this talk is an effort in this direction. So the next I'm going to our approach, how we do quantum circuit verification. So let's begin with this. This is also something that we are familiar with. So what is a whole triple? It just starts from a PQ, a pre-post condition, and S is the program you are going to verify. If the triple is valid, it means that from all state described by the precondition, P, after you run the circuit program S, it ends up with some state in Q. So that's a verification problem. In the quantum world, it's actually something very similar. P and Q are now set of quantum state, set of decision trees. And we need a way, we want to check whether after you run the program, the trees, all the trees that from the beginning, it end up with some tree is allowed by the post condition. And if we want to do this fully automatically, in order to do so, we need a good symbolic representation for a set of trees, set of quantum states. Our idea is to borrow idea from automata theory. So in a classical setting, the standard model to handle a set of words is regular language. That's what we know, or finite automata. Our idea is that the standard model to model a set of tree is actually regular tree language and tree automata. So that's what we use in this work. We use tree automata to model a set of quantum states. So that's the overview. So pre and post condition, they are tree automata. And we develop algorithms to compute the post. So for each gate, we know how to compute the next tree automata after we run the gate. So we do this like step by step. Then we get the set of states after I run the quantum circuit. And then I check whether all the states are within the post condition. So this is actually can be done by a standard tree automata language inclusion algorithm. So that's the overview. So we know how I do it. The next thing is that I want to show you why this is a good approach, give you some hint. So in order to do so, I need to show you how we use tree automata to encode a set of states. So this is an example of a singleton set, just one tree. So this tree, they have the same left and right tree. So 0, 0 has 50%, and 1, 0 has also 50%. They have the same left and right subtree. So I use this tree automata. So from the initial state, after take the first qubit, I go to the same state, Q0. The way to read it is that just glue this node to get the tree. So from Q, I go to Q0, the same subtree, and then from Q0, I can go to 1 and 2, where 1 is 50% and 2 is 0%. So by gluing this transition, I get the tree. And here you can see some sharding, so you can save some space. A more interesting example is I can use non-determinism to encode multiple states. In this case, I have encoded all 3 qubit basis state. Basis state means I have only one branch which has probability 1, and all the other branch has no probability. So this is the tree for 1, 1, 0 has probability 1, and all the other branch has no possibility. How I encode this in tree automata? So I just starting from the initial state, I make a non-deterministic choice. R1 means the one with 100% probability is on the right. So I have 2 choices, either on the right or on the left. If it is on the right, I make another non-deterministic choice and another non-deterministic choice. And 0 it means that below this, all the states are with no probability. And it ends with, if Q0, then I have 0 probability. Q1, I have 1 probability 1. And using this complex structure, I can use 11 transition to encode 8 states. It doesn't sound like quite right? 11 transition for 8 states is not so compact. But actually, I can generalize this structure. So for 2 to the n power of n quantum state, I can use only a linear number of transitions to encode it. So this is one example to show that it can be really very compact. It can be a compact representation of set of quantum states. And why? Because I can merge the shared structure within one state and also across different states. So that's why tree automata can be good here. And one thing to mention is that here I only use loop-free tree automata. And gate operation can be just tree automata transformation. For example, for X gate, the way to implement it is I just make a swap between, for example, if I want to apply the negation gate on the second qubit to swap the left and right tree, I just change the left and right node following the same qubit. So here I just change 1, 2 to 2, 1. This is simple. The other kind of gate is ZST gate. What they did is they multiply the coefficient of the sum subtree with multiply the probability of some subtree with some constant. what I'm doing is I just make a copy, the blue one. This is a copy of the original thing, and then multiply it with the C, and then glue it, like make a jump for all state with labeled with X1. I just make a jump on the right, jump to the blue version. And here, it looks like inefficient because I need to double the number of transition. But actually, I can reduce the automata size by some simulation-based minimization algorithm because these two trees, they share a lot of similarity in structure. And I need to refer you to like the paper for other gate operations, but that's everything that we can do. And actually, for the example that you have seen so far, the 3D are variables, are constant, but we can also extend it to variables to allow symbolic execution. This is actually an extension that will be presented in CAF this year. Okay, so I'll end up with some like evaluation result to show that it's also like good in practice, empirically. So the first set of example, we try it with some well-known quantum algorithms. Like we have Bernstein-Valiani, Grover search. This is a quantum version of set solving. And single means is with respect to one oracle, and O means that we test it against all possible oracle. And this is multi-control Toffoli. And the most interesting thing to see is that it's actually quite scalable. You can see this red bar here. We managed, the largest example we managed to try, the circuit we managed to verify is a 40 qubit circuit with more than 100,000 gates in roughly 10 minutes. So this is an example to show that, okay, it's actually quite efficient. And the other example, we show the capability of our approach in bug hunting. The way we do it is the following. So starting from some circuit, we inject the bug by randomly insert additional gate. And then we test the way that they are the same by testing them with different initial state, a sequence of different initial state. If one of them, we find that the final result, they are different, then they are different. And then we have a sequence, we have a strategy to generate an initial state. And this might be useful in like compiler validation. We check whether the result is correct after you run it. And but this approach can only be used to detect non-equivalence. It's not for equivalence checking. So we compare these with two state-of-the-art quantum equivalence checker, and they are based on different technology. Like primary is based on patch-sum, and QCEC is based on decision tree and the so-called DS calculus. It turns out that although our tool is not specialized for this kind of test, and it's actually quite efficient. The green color means that our approach has advantage. And the largest example we managed to find a bug is actually a 300 qubit circuit with roughly 1,000 gates here. So, so this is some like example to show that it's actually promising empirically also. Okay, so let me do a quick summary. So I think the most interesting part of this work is we find a link between two subjects that we thought they are irrelevant, automata theory and quantum computing. So far, we only tried the tree automata. This is the basic model to describe a set of trees, but we believe there's a lot of possibilities to follow up, and we are also interested to investigate this. And so far, the main reason we find for efficiency is the complex structure for tree automata. And and I would like to have more discussion because this is something like I find it new, and then probably it has some like more things to dig out. Yeah, that's it.
Hi, thanks for the talk. Charles Yuan, MIT. So Shor's algorithm for factoring an n-bit number requires time complexity of O of n cubed and space complexity of O of n. There are constant factors involved. The Google quantum team recently estimated that to factor a 1024-bit integer like RSA, it would take something around 3,000 qubits and tens of millions of quantum gates. My question is, do you envision that classical analysis approaches with exponentially scaling time complexity like your approach will be applicable to domains like factoring RSA, where a quantum computer is actually expected to offer an advantage over a classical computer?
I think this is a very good question. So, of course, if quantum computer is useful, it means that we have some computation that quantum computer can perform better than classical ones. And it seems contradictory that we use a classical computer to run exactly like what happened in quantum. So in order to verify this kind of let's say, examples that the quantum computer has an advantage, the only way, I think, for classical thing is we have maybe some abstraction technique, such that probably we don't really keep the exact state. Instead, we keep only the essential part for the correctness or some evidence for correctness. And here, this is just some starting point to show you that, okay, this is a way to do this. In order to make it really scalable for some example that is not possible for classical computing, we need something more. This is probably, you can just build this as one of the elements, or one step moving toward using classical verification technique to verify this kind of examples where quantum supremacy is there. You need to combine with several existing techniques in classical stuff. I mean, it's not there yet. Does this answer your question?
Thank you.
Yeah.
Hi, my name is Georg from University of Innsbruck. Thanks for the very nice talk. You mentioned equivalence tests for doing your verification. That means the no-cloning theorem you cannot test for, correct?
Sorry?
You cannot test for the no-cloning theorem. You cannot test whether there has been any copying done in the quantum circuit.
I probably didn't get, you say I can test the different copies of what?
No. Quantum mechanically, we cannot copy qubits. So the no-cloning theorem tells us that we cannot copy anything. This is not an equivalence test. Can you do validation of the no-cloning theorem?
I probably didn't completely get your question, but let me try to answer it. And if I didn't really address it correctly, we can talk about it offline. So you are talking about non-cloning, which means I cannot really make a copy of quantum state. But actually, I didn't really make a copy. Instead, I just start with the same equivalent set of initial state. I run it with these two different circuits. And at the end, I test classically with whether the final set of classical state, the set of trees, they are equivalent using classical algorithms. I really doesn't really run it in quantum computer. Everything is classical. So we don't face the problem of non-cloning in this setting.
Perhaps we can take this offline.
Yeah.
Thank you.
All right, let's check. Thank you, Yu-Fang, again.
Thank you.